Our topic today is fairness in machine learning, and our speaker today is Simon Couch. So Simon Couch is a software engineer at Posit, a coworker of mine. I'm really glad to have my coworker Simon here. So Simon is a software engineer at Posit, formerly our studio, where he works on the Tidy Models team. So Tidy Models, as I bet many of you are aware, is a framework, a collection of open source R packages for statistical modeling. So Simon's background is in statistics and sociology. And, one of the things I really appreciate about Simon is how Simon's perspective on how the tooling we build has a big impact on how like the nature of how we practice data science. So I will put in the link to Simon's blog so you can catch out the kind of work that he does. And Simon, we are so glad you're here. Thank you so much for coming and for preparing a talk. If you have a question as Simon goes through his talk, you can feel free to type in and we'll make sure, Simon, that you see it as we go about through the talk, and then we will hopefully have time for questions at the end as well. So Simon, welcome. We're so glad you're here.
Yeah, thank you for the very warm welcome. I really appreciate the chance to be here. As Julia said, my name is Simon. I work on open source statistical software at Posit. This is going to be a talk about fairness in machine learning. And specifically inside of the tidy models is the way that I'll be demonstrating it. So as Julia said, tidy models is an open source set of packages for machine learning in R. You can kind of think of the tidy models as a younger sibling to the tidyverse. It's developed by many of the same people. We use the same sort of software engineering principles to decide how we're going to implement things. And I'm really excited to be sharing about what we've been working on in the last year or so. Machine learning fairness is a research field that is quite varied. It reaches across a lot of different disciplines. A year or so ago, your very own Dr. Julia Silgi organized a reading group for folks across different groups at Posit to read about machine learning fairness and develop an understanding of the field. And since that reading group, we've worked on some functionality that we think is very principled and that we think will be really impactful for how people evaluate their machine learning models. So I'm going to be sharing some features that aren't yet in the production versions of the Tidy Models packages, but you can download the developmental versions of those packages using some links that I'll share here in a bit. All of these slides and the source code for these slides and some other resources where you can learn more about this talk are on the GitHub page simonpcouch/SLC-RUG/23. And I'll go to this page real quick just to show you some of the things that live inside of here. So the slides that I'm presenting with are publicly available, and I guess just to fact check, I'll share with them explicitly instead of the ones on my computer. These are HTML slides. They all the figures in this talk have alternative text, so if you use a screen reader, you should be able to navigate those well. These slides are based on an example analysis that we put together to demonstrate how to use these new tools. That blog post is going to the tidymodels.org site here soon, hopefully in the next couple of months. And so if you want a sort of annotated version of these slides later on, this blog post explains all the different things that I'll be walking through in this talk, and even has some bonus content for the sort of bigger picture of how to think about choosing fair models. And finally, if you want to learn more after looking through that analysis, there's another applied example that's a blog post that's forthcoming on the tidymodels.org website, and so that's linked in this third entry here. And if you want to install the versions of the packages that I'll be working with today, you can use the code here. So if you happen to miss that link, it will be in the bottom of the slides throughout the talk. And so you can type that in whenever if you want to check something out more thoroughly. So for a big picture overview of what I'm going to be talking about today, first I'm going to try to define what I mean when I talk about a machine learning model acting fairly. It turns out this is kind of the main subject of machine learning fairness as a field, is defining what we're actually talking about when we say that a model acts fairly or unfairly. Then I'll walk through that applied example I talked about. We'll give some context about the problem, do some EDA, make some plots, and then finally we'll move on to the fairness assessment, which uses those tools that are coming to the tidy models soon. And then we'll talk a little bit about how you can use those metrics to decide which machine learning model to use and how to communicate that model to people who might be using it. And lastly, I'll link out to some resources where you can learn more about that process. So let's start with fairness in machine learning. The idea of machine learning fairness is that machine learning models, we intend for them to be very good at picking up patterns. And um, uh, we find that an issue with machine learning models is also that they pick up patterns that might be patterns that we don't want them to pick up on. And so they can begin to encode injustices or biases that exist in our real world and reinforce them using the patterns that they find. Kind of the most notable example of this happening and something that brought a lot of attention to machine learning fairness as a research field is this article from ProPublica that came out in 2016. And this is kind of widely linked to probably in any talk or article you can come across about machine learning fairness. This team of independent investigators was exploring a model that's used in criminal sentencing across many jurisdictions in the US. The model attempts to predict whether a given person who's having an interaction with the criminal justice system is going to predict another crime in the future. And that output that predicts whether that person is going to commit another crime is used when they're determining the sentence for that person, when they're determining whether that person will be in pretrial detention or whether they can continue on living where they currently live until they're sentenced, so on and so forth. And these investigators found that given similar characteristics besides that person's race, if a person is Black, they're more likely to be predicted to commit a crime, all else being the same than a white person with similar demographic variables. Another set of examples that comes up again and again is around predictive policing. Predictive policing, the idea is that you want to predict when and where crime might happen. And if you can predict that, you can allocate police resources to have more presence in a given area. What we tend to find with these models is that if you allocate some portion of your policing resources to a given area, you'll continue to find more crime in that area. And your model will actually get pretty good because you're allocating all of your resources to this place where you always find more crime. And those places where you're allocating those resources are more likely to be poor. They're more likely to have populations other than white people living in them predominantly. Another example, this came out, I think, in 2018 about a recruiting tool that Amazon uses. So they process like hundreds of thousands of applications for their jobs every year. and they wanted to use AI to screen through resumes, develop scores, to help people decide whether a person ought to be interviewed or hired. And what they found was that there were all sorts of different ways that these models encoded first whether that person was a woman or not a woman, and then penalized different traits of applications that are typical to women and resulted in lower scores. So this is things like if that person attended a college that is historically a women's college, or if somebody describes themselves as like the team captain of the women's chess team or something like that. And even in things that are more minute, like the language that somebody uses to describe something that they did, they found that men were more likely to use words like executed or captured or something in the way that they described what their work was. And those words specifically were assigned a weight that resulted in resumes with those words in them being more highly rated. So across all of these examples, we see that these machine learning models find ways to encode patterns that exist in our society, and we may or may not want those patterns to be reflected in the way that a model makes predictions. So we need some way to evaluate whether a model aligns with our personal, morally held definition of fairness. I'm going to move on now to a question that might seem kind of weird. Right here, I have a graph that describes the behavior of a given machine learning model. On the x-axis is the true value of a vase. Imagine we're like manufacturing vases in some facility. We have a machine learning model that somehow predicts the weight of that vase using information like what materials it was made of, its volume, things like that. And what we see in this model specifically, so a perfect machine learning model, its predictions would live exactly along the dotted line, where a vase that's truly 100 grams, we would predict that it's 100 grams. A vase that's 500 grams, we would predict that it's 500. What this model actually does is it over predicts the mass of the vases that are quite light. So a vase that's 100 grams, we're predicting that it's more like 250. And the vice versa for the larger vases. We're predicting that a 500-gram vase is actually more something like 350. So the weird question that I have for y'all, and maybe you can just like give a thumbs up or a thumbs down in the chat, is this fair? Is this model acting fairly? Maybe thumbs up if you think it's fair to underpredict the weight of a vase, or thumbs down if you think it is unfair to the vase that is small to predict that it's actually heavier than it is. I'm seeing a good mix. Some people just like did it in camera too. I appreciate that. I'm gonna make the case that like I don't really care. I think this model isn't good. We should surely like fix this problem that we are observing. In statistics, the problem that we're observing is called regressivity, where we tend to predict values of our outcome that are closer to the mean. So if the distribution of masses of vases is something centered around 250, 300 grams, a machine learning model can do quite well, perform quite well by predicting values that are close to that average. So regressivity is a statistical property that we have defined measures to correct for. This data doesn't actually come from measuring the weight of vases. What we're talking about here are tax assessments of home values. So tax assessors' offices in jurisdictions across the US use machine learning models to attempt to estimate the value of homes, and a tendency of those models is to predict that the homes that are less expensive are actually are much closer to the mean, so it overvalues the value of those homes. And for homes that are more expensive, let's say closer to 500,000, that machine learning model tends to predict that the value of the home is much lower than it actually is. And so if your taxes are based on the assessed value of your home from this machine learning model, if I own a home that's $100,000, I'm being taxed at a rate that's 2.5 times the rate that a person with a median home value would see, and vice versa. So I would make the claim that this model is not acting fairly. The only thing that changed between our modeling problem of the vase weight and our modeling problem of the home value, the predictions are exactly the same, but the context change. And that changes my opinion of whether that model is acting fairly or unfairly. So when we're talking about a statistical property like regressivity, we have a measure for regressivity that we can maybe correct for given the appropriate machine learning model. When we're talking about fairness or unfairness, we don't have a tool that can be used across contexts, regardless of what we're measuring. The meaning of a fairness metric depends on how it's being applied. And so if you come out of this talk with anything, I would hope that it would be this idea that fairness is morally defined. We can try to operationalize it into a metric, and we can try to measure it, but the way that we measure that is always going to reflect our morally held values. And the corollary of this is thus machine learning fairness is not simply a mathematical optimization problem. So these like intense pink cranberry slides are going to mark moving from one section to the other, just in case you're feeling a little lost. So let's move on to our applied example problem. Now that we have a little bit of background on what model fairness actually means. In this applied example, we'll talk about measures that one can use to evaluate fairness in a context. But just as much as we do that, we're going to talk about the values that mathematically defined metric actually reflects in the real world. Okay. So a little over a year ago, and it's hard to believe that it was so recently, but ChatGPT celebrated its first birthday like a week or two ago. And the way that this tool works is you give it some sort of prompt and you ask it to write something for you, and it returns text that appears to be written by a human. You can ask it to write an essay for you of a given length, and given that prompt, it will return text for you. These models like have this gives an immediate reaction to a lot of people like, okay, in what context should something like this not be used, right? Like if we're evaluating people's writing and that evaluation is consequential anyway, we don't want people to be able to just turn in stuff that was written by ChatGPT. And so we see after ChatGPT is released, this wave of detectors, which given some set of input text, will try to predict whether that input text was written by ChatGPT or whether it was written by a human. And the media around this like started very positive and continues to be. People are like really excited or encouraged by this thought that we might be able to detect these things. ChatGPT themselves, the makers of ChatGPT, OpenAI, released their own model to try to detect that. I think this article, it's not in the screenshot, but I think this was in early 2023, so like soon after the release of the model itself. And we start to see this wave of kiddos in their college dorm rooms releasing these detectors that claim to be able to know when given input text is written by a model or written by a human. And so this Wired article reads, "The AI detection arms race is on. And this article in Nature is only from a month ago. The title reads, ChatGPT detector catches AI-generated papers with unprecedented accuracy. So it's really like a nice idea that we might be able to detect this. It would be probably good for the fair application of these tools, that we know when something is written by a ChatGPT or not. You know, it's obviously not always bad to have written something by ChatGPT, as long as you're citing your sources or whatnot. But if you're being evaluated in your writing, and you're turning in something that you didn't actually write, this is where that kind of moral quandary comes up. So it seems pretty cool. Um, I'm going to argue that it might not be. In the middle of 2023, sometime in the summer, OpenAI announced that they weren't going to develop their detector anymore, because they just found it too difficult a problem to solve. And it makes a lot of sense. ChatGPT is trained to give the most plausible sounding, most human written sounding answer it can come up with. It's not trained to give the most correct answer that it can come up with. And so it's consequently very hard to tell whether something was human written, because our goal in developing this thing was to make something that writes like a human. Another article, this is from pretty early in 2023. Professors are using ChatGPT detector tools to accuse students of cheating. What if the software is wrong? And this is exactly the question we should be asking. A month later, this article came out. This was actually like a preprint of a submitted paper, but then it got quite a bit of press. And this is one of those articles based on that paper. The title reads, AI detectors are biased against non-native English writers. So this like really caught my eye when this came out. I think it like came up on some social media feed, and I thought it was really interesting. It turns out these study authors posted all of their data and their code publicly, and so we were able to pull down all the data, tidy it up, and release it in an R package. And that R package will be subject of our analysis today. How did they make this claim that an AI detector is biased against non-native English writers? They first collected a corpus of essays that were actually written by humans. And they did this in a sort of stratified way. One portion of this sample is written by, quote, native English writers, and others that do not write English, quote unquote, natively. So I put this in quotes because the meaning of native English writer is not a given. And the study authors make some assumptions about what that means, and that's reflected in the source data. If you're more interested in looking into what we mean by native in this study's context, then I would encourage you to read that example analysis that we've linked to at the link down here. So they have a bunch of essays that are written by humans. The ones that are written by native English writers are like college application essays, state assessments for, I think it was like 8th graders or something like that. For the writers who don't write English natively, these were TOEFL applications, which is a standardized test used to determine whether a person who doesn't speak English natively is apparently prepared to take courses that are taught at an English-speaking university. And so there's a large sample of these essays that's available online. And then the next thing they do using ChatGPT, they generate many essays based on the same prompts that the college application essays and the TOEFL essays are based on. They either pass ChatGPT that prompt and they say, write an essay in response to this, or they pass the essay itself that was written by either a person who writes in English natively or not. And using that essay, they say, can you like refine this in some way? Can you write this more clearly? And so they're trying to best represent the kind of predominant modes in which somebody might make use of these tools to assist in their writing. And finally, they have this set of 7 GPT detectors that they buy subscriptions to, and they programmatically, through an API, pass all of these such and such thousand essays to these GPT detectors. And they say, is this written by a human or was this generated by a GPT? And so we end up with a data set that we'll be exploring today. I'm going to load the Tidy Models packages, and I'm also going to load this package called Detectors. You can install the Detectors package from CRAN, but it's also available at this link down below. So each row in this data set is a given essay that was passed to a given detector. So for this first essay, I have a AI written essay, and I have this prediction for whether that essay was written by AI or not. So pred AI is the probability that the essay was written by AI from a given detector. And then we can say, is that probability above or below 0.5? If the probability is above 0.5, we can just say that the hard class prediction is what we would call that, is that if I'm 99% sure that an essay was written by AI, the hard class prediction is that you wrote that essay using AI. And finally, the place that those predictions arrived from are noted in this detector column. So these are Sapling, Crossblade, Zero GPT. Those are 3 different marketed GPT detectors that we're passing these essays to see what their predictions will be. And finally, we have this column native, which encodes whether a person is assumed to be a native writer of English or not. So these first 2 are not native English writers. This third one is yes. And finally, this last one, NA, corresponds to an entry that was written by ChatGPT. So like ChatGPT is not necessarily a speaker of English or a speaker of not English, did not learn to write English in a given order. Maybe you can claim that they did, but the mathematical claim here is that it can't be both. And I'm pretty comfortable in that assertion. So we call that value missing. And we can do some basic EDA. This is a ggplot where I'm plotting the count of essays that were predicted to be generated by AI versus written by a human. On the right-hand side, we have the essays that were written by a native English writer. And so we can see there are quite a few more essays that are written by native English writers than not. And very, very few of them are predicted to be written by AI. On the left-hand side, there are quite fewer essays that were from that TOEFL sample. And we can see that most of them were predicted to be generated by AI. So just note, like all of these essays were written by humans that are contained in this plot. And so all of this, the colors in that bar should be all blue. But we're seeing that for whatever reason, these detectors are very bad at predicting whether an essay is written by a human or generated by GPT for people that don't write native Englishly. I knew I was going to do that. Don't write English natively in a way that they're not at all for people who do write natively, English natively. They're actually quite good. Instead of the classes, the hard class predictions, we can plot this using the probabilities. So this is split into 2 different panes. On the top pane, we have the distribution of probabilities that were for people that write English natively. And we can see that the probabilities are very close to zero for almost all of those people. In the bottom pane, it's the same exact plot. It's the distribution of probabilities, but this is for people who don't write English natively. And we can see that those probabilities are all across the board. And there's actually quite a few essays that are very confidently predicted to be written by people who don't write English natively, predicted to be written by AI that are actually written by a person. Your response to this might be, why are we aggregating across 7 different detectors, right? Like some detectors might be much better at this and have some data in their sample data and their training data than others. And so we can split this plot up into 7 different plots where each column is the given detector. I know this plot is very overwhelming, but just kind of focus in on one column at a time, and it's the same plot as before. In the top plots for people that write English natively, almost all of these detectors do very well and predict that this value of probability that it was generated by a GPT 0. And there's quite a bit of diversity in that sense for the non-native English writers. Most of these detectors are much more likely to predict that the essay was written by AI, but some of them seem to predict that it was written by a human just as often as they do for AI. And this one even predicts most essays were written by humans rather than AI. That is a good band name, isn't it? Okay, so we have a little bit of sense for how these distributions interact with each other. Now we'll move on to actually trying to assess fairness using the tidy models. So the question that we need to answer before we start calculating metrics is, what does it mean for a GPT detector to behave fairly? I'm going to present you 3 different perspectives for what a fair GPT detector might mean to you. This happens with me, and I'm assuming it's going to happen to you. I'm going to present this perspective, and you're going to think, oh, that makes sense. I do think that a GPT detector should behave that way. And we'll calculate a metric, and we'll see that we have a set of recommended models. These are the 3 best GPT detectors for that given criteria. And then if I show you the next one, you'll say, oh yeah, that's a very reasonable way to encode fairness for a GPT detector model. And we'll calculate that metric, and we'll take the top 3, and we'll see that we have a different set of recommended models than for the previous. And we'll do that 3 times, and we'll be a little confused, and then we'll clarify how to work from there. So this first position I call effective detection group blind. The position here is that it's unfair to pass on an essay written by a GPT as one's own work. I personally agree with this. If the evaluations for one's writing are pretty consequential, I think that passing your work on as your own, if it's written by a GPT, probably isn't fair. This position is represented in the interests of many people, right? A detector author has no idea what contexts their model is going to be used in. They probably should and train their models for specific contexts and market it only for that use. But these detector authors want their models to work well across many different contexts. So they might think, I'm going to train my model to detect GPT written content. A student might feel this way if they write their own essays and others are writing it using ChatGPT. They might think that this is unfair. And an instructor might feel this way. We haven't said anything about whether these given students are native writers of English or not, or whether there's a mix. But if this instructor is this instructor doesn't necessarily think that they want predictions to be different for native English writers versus not, that instructor might teach only students who don't write English natively or the other way around. Or they might not know that that these detectors behave this way. So to calculate the metrics for this position, we can just use any classical performance metric that we might use in another statistical modeling problem. How well does your model do is a question that can be addressed by many different metrics. Here we're going to use the ROC-AUC metric, or area under the receiver operating curve. The way that we do that is we start with the detector's data. Using dplyr, we group by that variable detector. We calculate this measure of how well the model is doing, and then we take the top 3 models. And so we have, as a result, this set of recommended models that maybe we should consider further. GPT-0 seems to do quite well. Originality AI seems to do quite well, and so does HF OpenAI. So we have this set of recommended models. I would note that these, as ROC AUC values go, 0.75, 0.68, 0.61 have a lot of work to do still. And so that should be part of your decision-making process. So there's one possible perspective. We're saying that a model should be able to detect GPT written work well, regardless of the context. And just note that this code makes no mention of that variable native. This code is possible with the CRAN versions of the Tidy Models packages. So you can do this without downloading anything fancy. Another perspective that we might have is that it's unfair to disproportionately classify human written text as AI generated for these different groups of people. If I'm disproportionately saying that text written by a person who does not write English natively is generated by AI, if I disproportionately predict that for that group of people rather than people that write English natively, I would say that's unfair. And there are many stakeholders who probably feel the same way, right? A student might feel this way. That could either be a person who writes in English natively who doesn't want undue harm on their classmates. That could be a student who does not write in English natively who doesn't want their work to be incorrectly flagged as written by a GPT. And another instructor or even the same instructor could probably hold this value too. I think this is kind of this would probably be a commonly held value across many people. One of the outputs of the research field of machine learning fairness is this wide range of different metrics. These metrics encode specific values in specific problem contexts. In our context, there's a fairness metric called equal opportunity that quantifies this definition. In the tidy models, we would use the equal opportunity function. We say we want equal opportunity by this variable native, and we create this new yardstick function. Yardstick is the package which assesses model performance in the tidy models. And this function is called equal opportunity by native. Equal opportunity is one of many fairness metrics in the developmental version of Yardstick. I would encourage you to check out that wider set at the links in the GitHub page. So we can do the same thing as before. We calculate a bunch of metrics for each detector, and then we take the top 3. And what we see, we haven't seen cross-plage before in the recommendations for models. We haven't seen 0 GPT before. We did see GPT-0 before, but that was in a different place in the rankings of those recommended models. So already what we're seeing is that these different morally held fairness values can be represented by different mathematical metrics, we might the values of these metrics might not be compatible in general. And so we need some way to incorporate these many understandings of fairness to decide which model we believe is most fair and how to communicate that. So in this example, the detectors with estimates closest to 0 are the most fair, and so cross-plage is the best, and so on. Finally, we'll talk through the position that it's unfair to pass on an essay written by a GPT as one's own work, so our first perspective, and it's unfair to disproportionately classify human written text as AI generated. So we want to balance these two notions of fairness somehow. I think many of us in the crowd could probably want to do both of those. And remember our second definition, it's unfair to disproportionately classify human written text as AI generated. What we're saying here is that we don't really care how well we do detect GPT written text. There's no measure for if an essay is written by a GPT, how well we can find it. And so we want to satisfy both of these. So the workflow here is to first ensure that a model detects GPT-generated work with some threshold of performance using our area under the receiver operating curve. And so we get that set of recommended models from before. Among that set of recommended models, which are the most fair? And so that encodes our second definition of fairness. I want to just take like 30 seconds and we can think about this. Using this workflow, which of these definitions of fairness is encoded as more important? Yeah, I would say go ahead and type it in the chat. I see one person thinks number one. Another way to phrase this question, by which of these definitions is it possible to like completely miss the most fair model? So we satisfied definition number one. Everybody's got it. We have that set of three, but among that set of three, it could be possible, and it's actually the case that the most fair model by this other definition doesn't make it into that set of three. So we're satisfying this first constraint first, and then we move on to the other. So we can do this by using the same code as before, finding the most performant detector using the area under the receiver operating curve. And then we can plug that set of three recommended models into the same code as before for equal opportunity. And we calculate the equal opportunity for each of those. And what we see is another set of three different recommended models by this notion of fairness. Little take-home work. If you want to switch the order of those steps, we can see if we get a different set of recommended models. Spoiler alert, you will. So that puts us in a difficult situation, right? Like we have these values of fairness and we want our model to act fairly if we're going to put it in a production context. But if those definitions of fairness are not morally or mathematically compatible in general, what do we do? And so the question of how we choose a detector is a question of what we value. In the applied examples that are linked on that GitHub page, I talk through different ways that we can weigh the importance of different metrics, that we can decide which metrics to use in the first place, that we can communicate what the use of those metrics means for different stakeholders that a model's predictions might affect. And so this isn't quite as like automatable as a typical machine learning analysis, where with the choice of a metric, there's a well-defined solution. What we're seeing here is that the choice of metric and the calculation of the metric and the definition of the metric depends on our morally held values. So if you're interested in learning more, I don't quite have time for this session to talk through how our values can be better represented by our choice of metrics, but those resources are linked there. If you want to learn more, so if you saw those plots that we were looking at before and you weren't sure how you might make like a bar plot using the tidyverse, or if the group by, summarize, arrange code that we saw when we were calculating metrics was unfamiliar to you, I would encourage you to check out the tidyverse book, R for Data Science. This is a great book to bring you from a novice tidyverse user to a fluent data analyst. And if you were unfamiliar with that ROC AUC code, or if I'm using words about machine learning that are unfamiliar to you, first, I apologize, but second, I will recommend you check out the book, Tidy Modeling with R. Oh, that's a nice alternative title, Tidily Modeling. Maybe that's grammatically incorrect. But that was written by Salt Lake City's own Dr. Julia Silge, so highly recommended. And if you want to learn more about how we're working to provide a sound toolkit to evaluate models with fairness in mind, I've linked out to some resources on this GitHub page. Keep an eye on our social media in the next few months. We're hoping to have this functionality out in the world sometime in January.
Awesome. Thank you so much, Simon. You probably have noticed the chat has been very busy. There's some questions. I just thank you so much. And so I'll dig into some questions if you're ready.
Yeah.
Okay, so Gwen asked, how can we know why the model is doing this? Like, how can we, like, the model was much more likely to predict that a something written by a non-native English
Mhm.
writer was from a GPT model. Do fairness metrics help us answer that question? Do the fairness metrics help us know why the model is behaving the way it does?
Yeah, I would say for the most part, the fairness metrics do not help. Um, uh, but insight into why and how the insight into the assumptions that a given modeling approach makes about how data is generated can help you understand why a model would make that given prediction. The original source paper that this data is from, and that's not linked to in this GitHub repository, but it is linked to in the documentation for the detectors R package. That original paper has some exploration into like why GPT models might behave this way, different measures that we can use to kind of anticipate when a model is going to predict that something is written by a GPT versus not.
Yeah, yeah. So, Dennis just right now asked a question that's exactly related to this. Like, what can you say maybe again, like what do fairness metrics do, and what does like explainable AI do? Like, where and are they related? Are they totally different? So, if we have questions about like model explainers, what do those do, and what do fairness metrics do?
Hmm. I would say they're absolutely kindred. Uh, in both, we want to understand how our problem context is kind of encoded into the modeling process, and better understand why and how our models are predicting in the way that they are. The why is more of explainable AI, and the how is more of the machine learning fairness side.
Awesome. I actually like that a lot. That's really great. Very early, towards the beginning of your talk, Kumar asked a question. How is this related to model calibration? Like how, when we do,
Mhm.
there are like these methods for model calibration, is it related at all? Um, uh, have you read anything about model calibration being related to fairness, or can you get more fair models by calibrating your
Mhm.
model? Like, what's the relationship between model calibration and these kinds of fairness metrics?
Totally. Yeah, it's very much related. So earlier on, I guess we can just scoot back to where that is now that those links have been up there for a good while. I show the original source data. So we have the prediction, predictive probability that something is written by AI, and then we have the class that we've assigned to that prediction. So for people that aren't familiar, calibration is focused on how do we set the threshold for whether something is predicted to be written by AI versus not of that probability. So in this source data, I chose zero point 0.5, as in if the predicted probability that something is written by AI is over zero point 0.5, I'm going to say that the thing is predicting that something was written by AI and vice versa. And we can vary the value of that threshold, and that changes the way that a model's predictions are understood to behave. So calibration is absolutely related. We have specified our tools in the tidy models in such a way that we want to make it very easy for people to make new fairness metrics because uh, problems like calibration uh, or encodings of our identities and our people groups in data vary so much from problem to problem that we need to be able to define our metrics specifically with that in mind. And so calibration is one of those reasons why we did that.
Awesome. John asked a question. So we are, as you when you learn about machine learning, you start hearing about all these metrics, and you're like, oh my gosh, what do these numbers mean? And accuracy is something we can usually get a handle on, right? Like zero is
Mhm.
bad, one is good. You're 100% right. Then you start learning about more things like ROCAUC, and you're like, okay, zero is bad, is like backwards. I've got it backwards. Half, I'm guessing. One is perfect. And then, so when you start thinking, we're learning about these new metrics. Is something like equality of opportunity? You said zero was good. Is it more like log loss, where it can actually be just to infinity? Like you could have 50 or 100, or is that like a good way to think about it? Is this like log loss, or is it 0 to 1? It's like 100% unfair versus
Mhm.
zero. Like, do you like how can we think about some of these metrics?
Yeah, yeah, that's a great question. Um, so in specifying what equal opportunity is in the tidy models, we had to make choices. And the choices that we make are somewhat related to how other packages do it in other languages. So specifically, FairLearn is a package that we look to quite a bit in Python. So you can the way that we've parameterized the equal opportunity, those values will always be in 0 to 1. I would say this is not an artifact of what equal opportunity means. It's an artifact of the way that we've programmed it. And if that is somehow limiting to you in your analysis, depending on what you're working on, we have tools to specify that in different ways.
Awesome. Awesome. There, have you seen example data sets for this kind of fairness work? I'm setting you up a little bit because I know the answer to this. For healthcare, should someone look for an exciting healthcare example to come out soon?
Yeah, Denise, you really set the ball on the tee for that. I'm very excited to see. So the other linked analysis on this GitHub page is based on an example in healthcare. Um, the focus of that analysis is on programs that hospital systems use to allocate resources, whether that be like the time of nurses and doctors or bed space or whatever it may be. They use machine learning models to help themselves decide who will get access to these additional care resources. And there have been many studies that have found that the training process for these models results in models that will, for two people that are equally sick, and that can be defined in many different ways. But for two people who are equally sick, a white person is more likely to be assigned those additional care resources than other people groups. The second example analysis that's coming up on the tidymodels.org page has a full-on training process. So that article, what we've done in this talk today, we haven't trained any models. We're using models that other people have trained and we're assessing them. This other article, we train our own models using the tidy models, and then we also use the tidy models to assess fairness. So I would very much recommend you check that out if you're interested in the healthcare context.
Awesome. Well, we're at the hour now, and we really like to keep people in and out because I know it's lunchtime or daytime for many of you who are in the US. So I have just a couple minutes that if people have questions, we can maybe stay for like another 5 minutes. I want to be respectful of your time as well, Simon. But we'll say thank you so much all to coming. Thank you, Simon, so much, and we'll wrap up our live stream and let you all be about on your day.
Yeah, thank you.